All right, so our next unit is about polynomial functions. Our first two units that we did, we really focused on quadratics, and that's specifically, those are a type of polynomial function where your highest power of x is 2. Okay, so it was always x squared and then whatever else. Okay, so the reason why we focus so much on those is that one, quadratics really model a lot of stuff that you see in real life, things that go up and come back down on different shapes. So you see those kind of cropping up a lot. And because they are the lowest power polynomial, right, you focused on all the linear stuff in Algebra 1, and then we spent a lot of time focusing on the quadratic stuff, which is power of x to the second power, at the beginning of Algebra 2. So now we're going to start kind of generalizing it. But because of the stuff that you've learned by looking at linear equations and then quadratic equations, you now have a pretty strong foundation to generalize that to all different types of polynomials. Okay, so we sort of focus on power of 1 and then power of 2, and then rather than focusing on like power of 3 and then power of 4, from here we're just going to start generalizing. Okay, so that's what we're looking at this one. So polynomials, okay, the definition of what a polynomial is, it's an expression or an equation in the form a sub n times x to the n power. Bear with me for now. I'll explain this in a minute. Plus a sub n minus 1 to the x sub n minus 1 plus a sub n minus 2 times x to the n minus 2, right? Plus, and then you follow that pattern until you get to a sub 1 times x to the first, and then plus a sub 0, technically times x to the 0, but anything to the 0 power is 1, so. Okay, so great. That looks like a mess. Okay, so what is going on here? So all the a sub whatevers, so a sub n minus 1, blah, 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 okay, those are all real numbers. Okay, so they have to be real numbers, no imaginaries. Okay, and whatever n is, that has to be a positive integer. Okay, and you're like, Miss King, that doesn't help. All right, so here's what's going on with this. Okay, when you have a polynomial, it's something like 3 times x to the fifth plus 2 times x to the fourth minus 4x to the third plus 6x plus 8. Okay, so what is going on in this thing is it's a generic form to say that these n minus 1, right, those are your exponents. And all that this is saying is it's saying a sub n is just standing for whatever the coefficient is in front of the variable of n power. Okay, so in this guy, since this one's x to the fifth, this would be a sub 5. This one's x to the fourth, so this would be a sub 4. This one's x to the third, so this would be a sub 3. This is x to the first, so that's a sub 1. And because there's no x squared term, we know that a sub 2 would be 0, right? That's why that term doesn't show up, because it's 0 x squared. Right? And then this guy is our constant, that's a sub 0, okay? So that's all that's going on here, right? These are just, they're matched to whatever variable it is, and it's just a way to reference the coefficient. The reason why you use this n minus 1, n minus 2 is because you don't know the starting number, right? If you're starting with n, all I know is that this one is whatever one number less than that is. I started with 5, so this is 5 minus 1, okay? So it's just a generic way of expressing any kind of a polynomial function like this. Okay? All right, so back to what our rules are. So all of the coefficients have to be real numbers, and whatever your n is, that has to be a positive integer. So you can't have like negative exponents. Okay? You can't have like fraction exponents and things like that, at least not in the variables. A sub n, so this guy at the front, we call that the leading coefficient. Okay, and then there's supposed to be a line here. All right, and then x is your variable. Okay. All right, so let's take a look at some examples and some not examples of polynomial functions. Okay, so something that would be considered a polynomial function, we could write out that whole thing that we just wrote. That's a polynomial function. Another shorter example would be like 3x to the fourth plus 2x squared. That one's a lot shorter, but it's a polynomial function because the coefficients in the front are real numbers, okay? n is a positive integer, so this guy right here is a positive integer, okay? So we've met our kind of requirements there. Another example of something that is a polynomial function would be like the square root of 2x cubed minus 1/5 x. Even though it's got a square root of 2, we've still met our conditions. That's one of my coefficients, and it's a real number, so we're okay. All right? If this was an exponent, we'd have a problem, but it's not, so we're good. Things that would not be considered polynomial equations, something like 3i times x squared, that is not a polynomial because it's got the imaginary number in it, and we have to have real coefficients. All right, and something like 3x squared plus 4x to the negative 1, right? That would not be considered a polynomial because my variable here is not positive. It's got to be a positive integer on the exponent, excuse me. All right, something similar, remember that is the same as writing 4 over x, right? So that would be a similar example where that is not a polynomial function because it's a x to the negative 1, even though it doesn't look like it. So your x's have to be up in like the top in the regular position. Okay, great. So that's kind of what we're talking about when we talk about polynomials. So a little bit more vocab that we have to go over down here. Standard form. Okay, standard form of a polynomial is when your polynomial is completely simplified. So it has to be completely simplified. Okay, and the exponents, okay, have to be in order from smallest to large, or no, I'm sorry, that's backwards. Largest to smallest. So from largest to smallest. Okay, so like this guy that we looked at, exponents go in order from biggest to smallest. No big deal. Okay, the degree of your polynomial, we talked about the degree of the polynomial, that is whatever your highest exponent is. Okay, at least it's the case when you only have one variable. Okay, if you have more than one variable, that makes things a little bit more complicated, but that is not what we're dealing with right now. So the degree is whatever your highest exponent is. Okay, and then each individual term, where terms are these little chunks, right? So each individual term also has a degree. Okay, so the degree of any given term is whatever the exponent on the variable is. Okay, so like the degree of this term is 3, the degree of that term is 5, the degree of that term is 0, and the degree of the entire polynomial is 5. It's whatever the biggest one is. Okay, great. All right, so when we graph polynomial functions, right, polynomial functions are just kind of, they're going to all look different. They're kind of wiggly and wavy, all right? So they're all going to kind of look a little bit different. And we're going to talk about what are some of the key features that you're going to see when you're looking at one of these graphs. Okay, so I'm going to give you just a generic sort of example. All right, so here's just an example of what a polynomial function might look like. Okay, they don't all look like this. Okay, so when we look at these, there's some features that you need to be aware of. First of all, this guy right here, that sort of looks like a vertex, but it's not really a vertex, right? And then similarly down here, it looks like a vertex, but it's really not, because to be a vertex, it has to be either the maximum or minimum point, and these ones aren't, right? This graph eventually goes higher than this, and it eventually goes lower than this one, okay? So I can't say that these are vertexes. So what we call this instead is we call this a local maximum. Okay, so it is not the maximum of the entire graph, but for the area that it's in, it is a maximum. Okay, and then similarly, this guy over here, we would call a local minimum. It's not the minimum of the whole graph, but it is for that particular area of the graph. All right, and then the other thing that we're going to be dealing with is we're going to be talking about where your graph is increasing and decreasing. We're going to focus on some notation for this, where we're going to look at interval notation again. But for right now, what I want you to just kind of focus on is we talk about how a graph is increasing and decreasing, and we reference what the x values are. Okay, so we talk about the increasing and decreasing, that has to deal with what the y values are doing, but we reference it with the x values. So for example, between this x value and this x value, so between those two x values, your graph is decreasing. Okay, so the height is decreasing from the x value of whatever this is to the x value of whatever that is. Okay, from there, right, from this point, so this x value going on, my graph is increasing, right, because it's going up. All right, and then here's the side that throws people off. On this side, right, we're talking about everything up to this x value. Your graph is also increasing here. Okay, so sometimes I see people say it's decreasing because they look at it as this x value going that way, right? But you're not. You're still following like how you read from left to right. So your graph is also increasing in that range. So it's going up, drops, it goes back up again. All right, so those are some of the key features that you're going to need to be aware of. Like I said, we're going to do more with this stuff going forward. Okay. All right, so let's talk about graphing on a calculator. Okay, so if I'm going to graph this polynomial on a calculator, what are the key things that we need to look for? Okay, so the first thing that you need to be aware of is that there is a theorem. It's called the fundamental theorem of algebra. Okay, and what this says is that a polynomial of degree n has at most n solutions or zeros. I don't know if there's an E after the O in zeros. Okay, you could also call those roots. I'm not sure I spelled zeros right. Zeros. Zero, but plural. Is there an E? I don't know. I don't think so, but maybe. Okay, so n solutions or n roots. Okay, what does that mean? So if you have a polynomial and the highest exponent is 5, it could have 5 solutions or 4 solutions or 3 solutions or 2 solutions or 1 solution or no solutions. Okay, but it can't have 6 solutions. Okay, this polynomial here is degree 4. It could have 4, 3, 2, 1, or 0 solutions, but it can't have 5, 6, or 7 solutions. Okay, so whatever your highest exponent is, that is the highest number of solutions that are possible, but it is not a guarantee that that's how many solutions there will be. And you know this from looking at our quadratics, right? When we looked at degree 2 polynomials, they could have 2 solutions, right? They could have 1 solution, or they could have no solution. So 2, 1, or 0, but there's no way for that graph to make 3 solutions. Okay? All right, so why do we bring that up? Because that's going to help us as we try to come up with viewing windows when we're looking at these polynomials. Okay? So grab your calculator. All right, and we are going to talk about what this is going to look like. I do not have my calculator right now, so I'm going to have to use my fancy phone, and hopefully you'll be able to see this. Okay, so first thing you're going to do, go to y equals, type in this equation. I know you can't see this on my phone right now, but it's all right. You know how to type it in. So x cubed minus 3x squared plus 3. Okay. So, all right, hang on. I'm going to see if I can... All right, I turned a light on and that helped a little bit. Okay, so this is just a standard viewing window. And I know this is so hard to see, but we got kicked out of school and I didn't get a chance to grab everything that I wanted. And one of those things was my calculator. So there we go. That kind of worked, right? Okay, so looking at this guy, right? I can see that there are 3 solutions here, right? There's 1, 2, 3 spots where it crosses the x-axis. So that's kind of my cue that I'm pretty sure I have the whole graph here, okay? So when I go to do my drawing of what this is going to look like, right, I can just set this up like normal, going from -10 to +10, okay? Give it a rough sketch of what it looks like, something like that. And I'm pretty confident that from here, these ends are just going to keep going in either direction, and I don't have to worry about anything else happening. All right, great. So let's look at this one. So same deal, go back, throw this into y equals. Hitting graph, waiting for the graph. Okay, so this is kind of what came up for me with just that standard viewing window. So what I'm looking at with this guy is, the question here is like, what's going on outside of this graph? I clearly can't see the whole thing, right? So here's what my question is. What happens with this graph? Does it just go like this? Is that all that this thing looks like? Or is there something else going on, right? Where I've got, I can see that there's solutions here, right? And I can see that I have 1, 2, 3 solutions just from kind of what I'm looking at. Okay, well, according to this rule, this has a degree of 5, which means it could have more answers than just this. Like, it's possible that this graph actually continues, and outside of my viewing window, it comes back down and goes back up. Okay, so this is the part where you have to kind of pay attention and you have to think about it. Okay, so what we want to kind of look at here is you want to use what you know about solutions to make sure you have them all. Okay, and I happen to know something extra about this one. See how there's a spot right there? Sorry, don't mind my notifications popping up. See how there's a spot right there where there's this weird kind of like squiggle thing that happens, right? So that weird kind of squiggle is the cue that you actually have a couple of imaginary solutions. Okay, so what's happening there is it's like every time you change direction, you get a new solution, right? So here I was going up and then I switched to going down, and that's how I'm getting these solutions, right? So what's kind of happening in this weird funky spot that goes like that is it's like the graph wants to turn around and it doesn't go all the way back up. Like, it starts to come back up to cross the x-axis, but doesn't quite make it. So that's your cue that you have imaginary solutions. Okay, so what this tells me is that I basically have the entire graph here. I just need to adjust a little bit up and down. So I'm going to just adjust my window really quick, change my height. I'm going to make it go up to maybe positive 15 and go down to maybe negative 20 and see where that ends me. There we go. And now I can see the whole thing. Okay, so I'm going to go ahead and graph this. All right, so here's what my graph looks like. Okay, I went from negative 10 to positive 10, and from negative 20 to positive 10. All right, and again, the key thing here, right, the thing that's helping me out is that I see this weird squiggle thing. Okay, so that right there, that is your cue, okay, that there are 2 imaginary solutions. Okay, so we have 2 imaginary solutions, and I know because of that weird squiggle thing. Okay, so that is kind of a, sorry, you couldn't see that. That's kind of a visual cue for you. All right, so the next thing we're gonna do is we're gonna talk about graphing by hand. So you're gonna wanna grab worksheet 4.1 because we're just gonna do some of the problems from that worksheet as kind of part of your notes. All right, so let's take a look at graphing these. So we're gonna look at an x cubed, x to the 4th, and x to the 5th function. And from there, we're gonna hopefully pick up on some patterns, okay? So x to the 3rd, when we go to graph this, we're gonna make a little table of values, no big deal. Negative 2 to the 3rd power, negative 8. Negative 1 to the 3rd power, negative 1. 0 to the 3rd is 0. 1 to the 3rd is 1. 2 to the 3rd is 8. Okay, so that's pretty straightforward and easy. I'm going to go ahead and plot those points. Here's negative 2, negative 8. Here's negative 1, negative 1, 0, 0, 1, 1, 2, 8. Okay, so that should be no big deal. Great. All right, so that's an x to the cube graph. So x to the 4th graph, these ones we haven't seen before. We've looked at x cubed before, but we haven't really done x to the 4th. Okay, so let's take a look at that one. So negative 2 to the 4th power, so that's 4 negative 2's multiplied together. So it's going to be positive 16. Negative 1 to the 4th power, 4 negative 1's will be a positive 1. And then 0, 1, 16. Okay, so we're going to go ahead and graph that. Note that on here, this axis now goes by 2's, right? So the x-axis is counting by 1 still, but the y-axis, these are counting by 2. So it's 0, 2, 4, 6, 8, 10, 12. All right, so negative 2, 16 is going to be about here. Negative 1 is going to be about there. Here's 0, 0, 1, 1. And 216 is up here. My copy of this did not print the coordinate planes great. They're a little bit tricky to read. All right. So that's what an x to the fourth graph looks like. Here's x to the fifth. So x to the fifth, negative 2 to the fifth power. So 5 negatives, that's going to multiply to a negative number, right? And then 5 2's multiplied together is going to be 32. So that's negative 32. Negative 1 to the fifth, that's going to be negative 1. 0, and then 1 and positive 32. All right, and then this graph, mine, again, it really printed weird on this one. So sorry, these ones still go by ones, but now these are going by fives. So we're going to eyeball it. So negative 2, and then negative 32, 5, 10, 15, 20, 25, 30. So 32 is going to be about, I don't know, there-ish, right? Okay, negative 1 is going to be about there-ish. 0, 0 is nice and easy. 1, 1 is about there-ish. And then 2, positive 32 will be about there. So that's what this graph looks like. Okay, great. Well, something to notice about this, and hopefully you kind of picked up on this a little bit on your own, but if you sort of step back and look at these guys, right, you can kind of see some patterns here. Like the x to the third and the x to the fifth look a lot alike. And x to the fourth looks an awful lot like an x squared graph, right? Okay, and if you kind of think about it, that pattern is going to continue because the thing that distinguishes and makes them look either like this squiggle shape or this is if it's an even or an odd exponent, right? The odd exponents, the negatives end up negative, right? And that makes the squiggle. The even exponents, everything becomes positive and that makes it U-shaped. Okay, so when we look at these, we can determine a couple of things about our graph just by looking at this, right? I can go based off of these, I can tell sort of generally what the graph is going to look like. Now, if I start adding in like an x to the third and an x to the second to one of these, that's going to change things. But when we're just talking x to some power, you can make a pretty good prediction about what your graph is going to look like. Okay, we're going to talk about that more later and how you can use that knowledge to your advantage. All right, so let's talk about graphing some of these, okay? So we're gonna look at graphs using our transformations. Remember we did transformations unit 1? And I was like, guys, we're gonna see this like the whole year? Guys, we're seeing this the whole year. All right, so this guy right here, right? This is the same transformations that we've been doing. The negative in the front tells me that I have a vertical flip. So I'm using the same table of values that we had before. Here's an x to the fourth. Here's my table of values, but I'm doing a vertical flip. So what I'm going to do is I'm going to plot these points, but anytime I would have gone up, I'll go down instead. And anytime I would have gone down, I'll go up instead. So negative 2, positive 16, I'm going to go down instead. Negative 2, negative 16. 2, 4, 6, 8, 10, 12, 14, 16. Sorry, I can't read these numbers. So there's that guy. Negative 1, 1 is going to become negative 1, negative 1. Okay, 0, 0, that'll stay the same, right? I'm going the opposite direction, right? So it's going over 1 instead of going up 1, I'm going to go down 1. Over 2, and instead of up 16, down 16. And there's my graph. All right, great. Next one, x minus 2 to the third power. So I know I'm going to need this table of values because I'm talking about something cubed, right? And I know that this is going to do a left-right shift and it's backwards of what you'd think. So that is going to take me to the right 2. Okay, so what I'm going to do for this guy is I'm going to start by just moving my 0, 0 to the right 2. So there's my new, oop, that is definitely left. Sorry. This way, that's right 2. Okay, and then from there, I'll just plot my points using my new modified table of values. So negative 2, negative 8, negative 2, 2, 4, 6, 8 would be here, right? Negative 1 would be here. 1, 1's here. And then 2, 8 would be there. And there's my graph. Okay, and you can see how it looks exactly like this one, just shifted over a little bit. Okay, great. All right, this next one here, this is also an x cubed, so I'm still using this table of values, but this time we are shifting it down 2, right? So this is shifting down 2. So the first thing I'm going to do is I'm going to move my origin down 2. That is here because these are numbered by 2s. Okay, and then I can just plot the rest of these points like normal. So -2, -8, 4, 6, 8 would be about there, right? -1, -1, 0, 0 we already got, 1, 1, and then 2, 8. And there we go. Okay, so you can see how these things are going, and they're going to behave exactly the same way that we've done this, okay? So you've got 5 more graphs on here to finish off for your homework, where you're just going to shift these around, okay? And they're going to behave just like your normal shifts always were. That's kind of the beauty of transformations and using a modified table of values, is that you learn it the first time, and then it applies in a lot of different places.